Plasmodium falciparum is a parasite that causes malaria and is transmitted through the bites of Anopheles mosquitoes. Researchers demonstrate that exposure to Atovaquone, otherwise known as ATQ, shortly before or after Plasmodium falciparum infection leads to full parasite arrest in the midgut, preventing the transmission of malaria. This drug can be administered when Anopheles gambae mosquitoes take up ATQ from the treated surfaces through their legs. Moving on, we have the development of the parasites. You can see on this slide the target of ATQ administration. Uninfected female mosquitoes, mosquito bites, and infected human host. And then to move on to mosquito absorbs gametocytes from human host, which goes in the stomach of the mosquito. And gametocytes merge and turn into an oconite, which turn into a cyst on the stomach wall of the mosquito. Parasites were killed at the early zygote oconite transition as determined by immunofluorescent arrays of infected midguts, which you can see in the figure. So
ATQ is a specific inhibitor of the parasite cytochrome BC1 complex in Plasmodium falciparum. It targets the cytochrome BC1 complex, disrupting mitochondrial electron transport and hindering energy metabolism, effectively inhibiting the parasite's vital functions. This study has shown that incorporating Plasmodium inhibitors into long-lasting insecticide-treated bed nets, or LLINs, could substantially mitigate insecticide resistance, providing a strong method to halt malaria transmission and support eradication initiatives.
Okay, so now I'm going to talk about testing the anti-malarial compounds, the experimental methods, and analysis. The intervention described in this study involved conducting experiments in order to assess the effectiveness of certain compounds in reducing the malaria transmission by Anopheles gambae mosquitoes. To ensure the robustness of their experimental design, they conducted a power analysis in order to determine the minimum sample sizes required to detect reductions in both oocyst intensity and prevalence. Randomization was employed in order to allocate mosquitoes to treatment groups, ensuring an unbiased assignment. Due to biosafety regulations, blinding during data collection was limited. However, steps were taken to maintain impartiality in reporting the results. Their mosquito insect lines were carefully maintained under controlled conditions, and compound exposures were meticulously executed in order to assure an accurate assessment. P. falciparum infection assays were conducted by exposing mosquitoes to compounds and then to parasites, followed by a rigorous assessment of infection prevalence and intensity. They also used oconite immunofluorescent staining in order to detect the parasite forms within the mosquito midguts. Survival assays were conducted to evaluate both acute and long-term survival post-exposure to compounds. An egg development assay was performed in order to assess the impacts of compounds on a mosquito egg development. Additionally, mathematical modeling was employed in order to predict the potential effect of adding antimalarial compounds to bed nets. So now talking more about the data techniques, the statistical analysis were carried out using GraphPad Prism version 7.0 and JMP Pro 14 with experiments replicated independently multiple times. All custom code used in the study has been uploaded to GitHub for accessibility, and raw data for infection experiments are available as supplementary data.
And so now we can move on to the results. And so in this first graph, or figure, we have the relationship between ATQ concentration and oocyst prevalence. And it's 4 separate graphs, and on the left side of each graph we have the control group, and which is just received no ATQ. It's mosquitoes receiving ATQ. And on the right side we have the concentration of ATQ that the mosquitoes received. And so as we see decreasing concentrations of ATQ going from the left graph to the right, we can see that the oocyst intensity and prevalence does increase And so that does show that there's less Plasmodium falciparum development, and it also shows that increasing ATQ concentration does cause decreased oocyst prevalence in the midgut. So in this second figure here, we can see the Plasmodium falciparum life stage prevalence in the midgut of the mosquitoes. And so if you look at the graph on the left, we can see the control group and the group that was administered ATQ. And we can see that the eukaryotes are almost completely gone. And that's a key stage in the development of the sporozoites, which eventually go into the salivary glands of the mosquitoes. And so what this tells us is that the ATQ does act on the eukaryote stage of the mosquitoes, or of the malaria. And if you look at the pictures on the right here, this is of the mosquito midgut. And the right arrows are retorts, and the asterisk is a zygote, but there's no eukaryote prevalence. And you can see here on the left side, control group, which there is. And so in this final figure here, we look at the relationship of ATQ, time of exposure, and its effectiveness. And so if we look at the left graph, we can see that they were administered ATQ 24 hours before their infection. And when you compare the control group to the experimental, we can see that the oocyst intensity is 0. And so that shows that it's still still very effective 24 hours before infection. And if you look at the graph on the right, we can see that they were exposed to ATQ 12 hours post-infection. And this graph also shows that there is a 0% oocyst intensity. And so this shows that it's just as effective when the mosquitoes are exposed 24 hours before or 12 hours after infection, which is important information when we're thinking about when the mosquitoes might land on the nets and come into contact with ATQ, and if they're already exposed to malaria at that time.
This drug can be implemented in such a way that when the female mosquito lands on something with ATQ, it'll act in a way that helps prevent infection in gambiots. These findings indicate that the ATQ-like antimalarials could be incorporated into control interventions other than treated nets, such as attractive toxic sugar baits in which female mosquitoes become exposed to chemicals while feeding on sugar, or indoor residual insecticide spraying in which contact occurs while female mosquitoes are resting before or after blood feeding. In this diagram, we see that the ATQ exposure has no effect on the acute or long-term survival of A. gambiae female mosquitoes. The production of eggs after an infected blood meal is not affected by the ATQ. In this specific figure, we can see that the addition of ATQ to insecticides helps to decrease the spread of malaria, and in some cases decreases to 0 or almost 0. Our y-axis represents the resistance to insecticides, and then the x-axis represents the coverage percent of the insecticide or the insecticide with ATQ-like compounds. We see that the coverage of our insecticide and ATQ-like compound in both 20% malaria prevalence and 70%, there's an increase in effectiveness, showing that with the ATQ added, even as insecticide resistance increases, the added ATQ-like compound shows 100% effectiveness. With insecticide only in both 20% and 70% malaria prevalence, we see that the effectiveness is much lower than with the ATQ.
While the use of ATQ to prevent malaria transmission in a proof-of-concept study has shown considerable results, there are still a number of unexplored variables that may lead to this treatment being less effective than anticipated. Factors that need further experimentation include cost and formulation, or whether ATQ can be produced in an efficient enough manner for widespread use, stability, or how long ATQ can remain on a surface before becoming ineffective, and toxicity, including what other effects ATQ may have on both humans and the surfaces and environments it is applied on. It is also worth noting that the widespread use of ATQ may be inadvisable due to the increased potential for mutations to arise compromising the effectiveness of this compound, which would be problematic as ATQ is commonly used in the treatment of malaria, and increasing the likelihood of a resistance to it would ultimately be a step backwards in the fight against this parasite.
As for future implementation, this study's results demonstrate that adding an ATQ-like compound to insecticide-treated nets significantly enhances their ability to reduce malarial transmission. The malaria transmission model used in the study covers coverage levels, insecticide resistance, and human infection prevalence. The graphs illustrate that nets treated with a combination of insecticides and ATQ consistently outperform those treated with insecticide alone, indicating the potential broad applicability and effectiveness of this approach in malarial control. In the future, researchers can collaborate with public health workers to implement insecticides in indoor spraying of house walls, integration of ATQ to long-lasting insecticide-treated bed nets, and attractive toxic sugar baits, in which female mosquitoes become exposed to chemicals while feeding on sugar before blood meals. To reiterate, The main experiment was conducted by the authors to assess the impact of Atovaquone on transmission of Plasmodium falciparum parasites through Anopheles gambiae mosquitoes. The statistically significant results collected throughout the experiment demonstrate ATQ's potential to effectively reduce malaria transmission. Mathematical modeling supports the incorporation of these compounds into bed nets for enhanced efficacy. ATQ induced full inhibition of P. falciparum infection, meaning that there is 100% protection against infection on the same day of exposure. Barriers for Atovaquone include potential resistance development due to mutations in the cytochrome B gene. However, its mechanism of inhibiting the parasite cytochrome BC1 complex presents long-term potential for malaria treatment by providing a foundation for the development of new, effective anti-malarial drugs.